All right, today we're going to go over the homework, but just a couple problems on the homework, and then we're going to spend the rest of the time before we take our quiz prepping by doing questions that will be similar to the questions we're going to see on the quiz. You're then going to take the quiz. It'll take the remainder of the class period, and we won't be able to get to the lesson, but that's okay because you guys are going to forget whatever I tell you over the Thanksgiving break, and then you'll have to watch the video anyways. So this way you just watch the video and you'll be super prepared for the quiz today. So we're going to start out by doing number 86 from your homework. So I wanted to do this because it both dealt with taking a derivative and then analyzing the derivative and the second derivative. 86 from the first section asks you to find the relative extrema as well as the points of inflection. Okay? So to find the relative extrema, we're first going to analyze the signs of my first derivative. To analyze the signs of your first derivative, you're going to take the derivative and set it equal to 0. So we're going to use the quotient rule. Derivative of log x is 1 over x. That's the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. I can simplify this. The 1 over x times x is just 1. So I got 1 minus log x over x squared. Okay, I will set this equal to 0, or I will see when it's undefined. Now, since we have the function y equals log x over x, we should remember that we are not allowed to plug in any negative values or 0 into log x. So our domain is restricted to just x's greater than 0. So yes, the denominator will equal 0 when x is 0. However, on our number line, we're just going to start with 0 anyways because we have log x. Okay, so really, I'm going to just worry about when the numerator is equal to 0. Numerator is 1 minus log x. I will set that equal to 0. I can add log x to both sides. Now, how do I solve for log x in this situation? How do I get x by itself when it's inside of log? Yeah, you're not going to multiply both sides by e. You're just going to take both sides to the power of e. So you go e to the power and e to the power. E to the log x will just be x. And then on the left side, e to the first is just e. So that is my first critical point for y prime when x is e. Question? Exactly. If I had e to the power, and that's equal to some value, you would take the log of both sides to get x equals the log of 5. Okay? Okay, so let's go back to the derivative. So here is the derivative. This is the simplified derivative. Now, I need to use test points to figure out the signs of the first derivative around 0 and e. Well, first thing I know is that whenever I plug in positive values into the denominator, it will be positive. So I know the denominator will always be positive because it's just x squared. So I'm really just going to worry about the numerator, 1 minus log x. Now, here's the key. When you are testing your signs of stuff with logs in it, use powers of e. Why do we use powers of e? Because we know that the log of a power of e is just the number. Log and e will undo each other. So the log of e squared is just 2. The log of 1 over e, that's the same as the log of e to the negative first. That is negative 1. Okay? So that is what I'm going to use for test points. I'm going to use a value like e to the negative first. and e squared. Those are values that will help me determine the sign of 1 minus log x. So I will start by using e to the negative first. 1 minus log of e to the negative first would be 1 minus negative 1. That is a positive 2. So I know that all signs of my first derivative will be positive between 0 and e. Then I will check e squared. 1 minus log of e squared is 1 minus 2. That is negative 1. Therefore, those are the signs of all of my first derivatives when x is bigger than e. You're asked to find the relative extrema for your original function y equals log x over x. Well, it looks like we have a relative max at e. Why do we have a relative max? Because y prime changes sign from positive to negative at that location. Okay, that means y is increasing from 0 to e, and then y is decreasing after e. Now we have to move to the second derivative to find the points of inflection. So I'm going to use this first derivative to find the second derivative. Second derivative, you will use the quotient rule again. It's the derivative of the top, so that would be negative 1 over x times the bottom, x squared, minus the derivative of the bottom, 2x, times the top, 1 minus log x. That is all over the bottom squared. Okay, now again, I will set that equal to 0 or c when it's undefined. Well, again, we'll have the denominator equal to 0 when x is 0, but that's fine. I'm going to start with 0 anyways because that's in my that's where my domain begins. I'm going to simplify this. I'll just have negative x minus 2x times 1 minus log x over x to the fourth. I notice that I can factor out an x from the numerator. So I'll have x times negative 1 minus 2 times 1 minus log x over x to the fourth. Cancel that x with one of the x's in the denominator. And we will set this equal to 0. So again, 0 is where we're going to start. We're going to analyze the signs of my second derivative. But we need to find if there's any other locations where we're equal to 0. So I need to solve the numerator set equal to 0. I'll distribute the negative 2. I'll then add the negative 1 and the negative 2. And I'll solve for x. I would add 3. Divide by 2, log x will be equal to positive 3 over 2. I would then take e to the power of both sides to get rid of the log, and I'd have x is equal to e to the 3 halves. So here, we'd have e to the 3 halves. Now, again, we need to test the signs of my second derivative. I will use values like e to the negative first, or just e, and then e squared. I'll plug it into my second derivative. Again, since it's a positive value, the denominator will remain positive. So I really have to worry about just the numerator. This is the simplified numerator for y double prime. When I plug in e to the negative first, I get negative 3 plus 2 times the log of e to the negative first. That's negative 3 times 2, or negative 3 plus 2 times negative 1. So that's negative 3 plus negative 2, that's negative 5, that is negative. I'll try the second derivative at e squared. That'd be negative 3 plus 2 log of e squared. That would just be negative 3 plus 2 times 2. That's 4 plus negative 3, that is positive. So now I see that my original function y will be concave down between 0 and e to the 3 halves. It'll be concave up after 3 halves, and this would be a point of inflection. Okay, that is unit 4 in a nutshell, only with logs. Let's practice unit 4 with e's. So we had a problem on the other section number 70, x e to the negative x? I do.
Thank you, sir.
You're welcome. So let's look at negative number 70 from the other section. Same problem. We're asked to find the relative extrema as well as the points of inflection. We have x e to the negative x. Well, same process. We're going to start by taking the derivative, setting it equal to 0 or seeing when it's undefined. Use the product rule here. So the derivative of x is 1 times e to the negative x. That's the derivative of the first times the second. Plus the derivative of e to the negative x. Okay, let's remember the derivative of e to a power is just e to the power. So using the chain rule, the derivative of e to the negative x would be e to the negative x times the derivative of negative x, which is negative 1. And that'd be multiplied by x. Okay, I'll set that equal to 0 or see when it's undefined. It'll never be undefined. There's no denominator because e is always going to be positive. Now this looks crazy. It looks like it's going to be tough to solve, but I just have to factor out an e to the negative x. And let's see what I have. That. Well, even still, you might think, well, this is a problem. I don't know when this is 0. Well, it's never 0. This is always positive for any x. Doesn't matter what x you use. You can use 0. E to the 0 is 1. You can use any value. You would end up with a positive y value. So that's always positive. So we just have to worry about this. And we figure out when x is 1, this entire thing will be equal to 0.
Why is there a negative 1 when you
the derivative of e to the negative x is e to the negative x times negative 1. Right? That's
for everything with the multiply, like x times something.
so if I had e to the 3x, the derivative of e to the 3x would be e to the 3x times the derivative of 3x, which is 3. If it was e to the 3x squared, it'd be e to the 3x squared times 6x. Chain rule. Derivative of the outside, leave the inside, times the derivative of the inside. Okay? So we got x equals 1 as our critical point. We'll analyze the signs of f prime in this case around 1. Now in this situation, you can plug in any x's. There's no restrictions on the domain. X can be any real number. Okay, it's not just bigger than 0. So I will look at any value to the left of 1, but I can just choose 0. And any value to the right of 1, I can choose something like 2. E to the negative x is always positive. If I plug in 0, it would just be 1. If I plug in 0 here, I just have 1. So this is positive. If I plug in something like 2, this would still be positive. It'd be e to the negative second, which is just 1 over e squared, which is just a decimal, but it's still positive. Then I plug in 2 over here, I'd have negative 2 plus 1, which is negative 1, so it's negative. So we just found that f, the original function, will have a relative max at 1. F is increasing to the left of 1, f is decreasing to the right of 1. Okay, let's look at the second derivative to find the points of inflection. Well, here is my first derivative. I can maybe make it look a little nicer, put this as a negative x in front of the e to the x, e to the negative x. This would be a product. We'd have to make sure we knew that's a product. The derivative of e to the negative x, again, is e to the negative x times negative 1, chain rule. Okay, the derivative of this, using the product rule, would be the derivative of negative x, which is negative 1, times e to the negative x, plus the derivative of e to the negative x, that'd be e to the negative x times negative 1, times the first guy, which is negative x. Okay, and I'll set that equal to 0. This looks really, really tough and really, really challenging. But we should notice that every single term has an e to the negative x in it. So we can just get rid of it. Not really get rid of it, but factor it out. And then I'd have -1 here, I'd have -1 here, and I'd have a positive x here. So I'd have e to the -x times -2 plus x. I can solve for x. X is just equal to 2. There are no other values for x that will make this left side equal to 0 because this is always positive. So I then can analyze the signs of my second derivative around 2 using this simplified second derivative. If I plugged in a value like 3, it would be positive. If I plugged in a value like 0, it would be negative. Therefore, we have a point of inflection at 2 because the original function f will be concave down to the left of 2, and the original function f would be concave up to the right of 2. Okay, those two problems are very, very, not very, very, I would say those problems are definitely inside the realm of difficulty that you will see on the quiz, okay? We're going to do now practice problems that are also just like those problems and a little bit different, covering everything, just random derivatives, limits, problems just like that, and that will be, that will prepare you for your quiz. So let's do it. Let's do this one. So the function is x squared e to the x. The question is, when is f of x decreasing? Yep. Remember, after you find your derivative, if you have a term that is in both of your terms, you can factor it out. You'll see an e to the x in both of your terms. So go ahead and factor it out. That's when the derivative is equal to 0, but that's what you need to find to examine the signs of your derivative. The signs of your derivative will tell you if your original function is increasing or decreasing. I pick a value like 3. I know that e to the x is always positive. So I pick 3, positive, positive, positive. I pick -1. Positive, negative, positive. I pick -3, positive, negative, negative. When are we decreasing? We are decreasing between -2 and 0. Any questions about that? Okay. If f of x is equal to x log x, when is f of x increasing. Okay, I need to find when f is increasing. That's when f prime is positive. How do you find when something's positive? Start by setting the derivative equal to 0, then examine your signs around that. So, the derivative, f prime g plus g prime f. You get that. Make sure everybody gets that. I'm going to set that equal to 0. I get this. How do I solve for x? E to the power of both sides. Not just e times both sides. It's different. E to the power. And you get x equals e to the negative first, which is the same as 1 over e. Question? You can't plug in negative values into the natural log, but natural log can be any negative value. So I can't take the log of -1. That doesn't exist. But turns out the log of 1 over e gives us -1. So remember the graph of log of x, it looks like this. That means any y value really will be touched by some x value as an input. Okay, it's just you want to go to negative values, you're going to have to be to the left of 1. So between 0 and 1, we'll have negative y values. For positive y values, we'll have to be greater than 1. So I get x equals 1 over e. Now, if you didn't get that, well, you have it now. Let's go ahead and all examine the signs of my derivative around 1 over e. Now, this is a function with the log x, so we should know that our domain is restricted to x's bigger than 0. Go ahead and pick a couple test points. And go from there. I don't know why I set that equal to 0. I'm just trying to find the sign of it. This I know is less than 0. This I know is greater than 0. That's negative. That's positive. All right, so when is this function x log x increasing? When x is greater than 1 over e. Question?
Well, the log of e to the power cancels out that, I guess.
Yep. The log of e to a power is just the power. Logs and e's are inverses of each other, so they undo what the other one is doing. Now you have to be using them in the correct way. You take log of x is equal to 5. I'm not going to say e times 5 is equal to x. It would be e to the power, because y equals e to the x and y equals log x are inverses. Okay? Okay, let's try a similar problem. Let's go back to the E world. We did a problem like this in our notes last class. You'll see a problem like this on your quiz today. K is just a constant. X squared e to the kx, we are told, has a critical point when x is 4. We want to find k to make sure this is true. Critical point is when your derivative will equal 0 or undefined. We should remember that. Talk about the derivative of e to the kx. Well, maybe if I use the number, it'll help me. The derivative of e to the 3x is just e to the power times the derivative of the power. So the derivative of e to the kx would be e to the power times the derivative of the power. Since k is just a number, it'd be e to the kx times k. Now, we are told that this function has a critical point when x is 4. That means this f prime at 4 has to equal 0. Well, I could plug in 4 everywhere. Get 8 e to the k times 4 plus e to the k times 4 times k times 16. That guy on the right's got to equal 0. So that means I just need to solve for k. Well, I have k here, and k here. How do I solve for k? Well, I'm going to start by factoring out the e to the k times 4. No matter what k is, e to the 4k will always be positive. That means you just have to worry about when this is 0. When is that? When k is -1/2. Any questions about that? Yes, Ms. Street. Yeah, you could have factored out the e to the kx first and then plugged in 4 everywhere. Yep. You could have even like kind of forgotten about it since you know it'll never equal 0. Any other questions? All right. Another problem with logs. Do this problem. Key to this problem is you're asking when f is increasing, you know that's when f prime is positive, you are given f prime. You don't have to take the derivative of this. That is f prime. You don't know what the original function is, but you know what the derivative is. So all you need to do is examine the signs of your derivative by first setting it equal to 0 and then testing your intervals. We get when x is e, we will be equal to 0. Now, since this derivative is, well, we're told in the question that x has to be bigger than 0. So start out with 0. Must be because the original function has log in it. We will then test powers of e, because they're easy to work with, as my test points. E to the negative first plugged in here would be 1 minus negative 1, positive. E to the second plugged into my derivative, 1 minus 2, negative. When are we increasing? We are increasing between 0 and e. Questions about that? Okay, those are kind of the more advanced type of problems that we will see. Let's go to certain easier problems. Yes, question before we get there. I used the test point e to the negative first. I plugged it in here. 1 minus log of e to the negative first is 1 minus negative 1. That's positive. So the signs of my derivatives between 0 and e, since the sign of the derivative at e is 0, all of the signs here are going to be positive. That's where I must be increasing. Does that help? Okay. All right, let's go and do like a limit problem. You might have a limit problem on your quiz today that deals with e's or logs. Different ways to do this. You can rewrite it, talking about the limit as x approaches positive infinity. You know that this would stay as x squared, but this would be changed into e to the positive x in a denominator. Now, if you look at the comparison of the growth, this is growing slower than this. Since this is growing faster than this, we'll have a bigger number in the denominator divided into a smaller number, which means this would be a small decimal getting smaller and smaller and smaller, approaching 0. Or another way to think about it, sometimes with limits you like to just plug in stuff. So you got like negative infinity squared and then e to the negative infinity. Well, sure, you got a big number being squared, but that underneath e to a big number, this would be larger in terms of its growth compared to this, which is another way you can think of that being 0. Okay. Always a problem seen on the AP test, limits at negative infinity of things where x is in an exponent. Any questions about that? Yes? Right, that was always the first step for limits. If I have the limit as x approaches 1 of x minus 2 over x squared minus 4, actually the first step would be to plug in 1 and see if this function exists at 1. But with infinity, it's a little bit different. With infinity, you kind of have to think about the growth of certain things. So there are these rules. So if I had, the limit as x approaches infinity of x to the 100th over e to the x, we should know that the growth of e to the x is much faster than the growth of x to the 100th. So eventually, as I plug in bigger and bigger values for x, this will grow faster and faster. This will be a bigger number than this. This will then be a decimal that would be approaching 0. So we looked at the growth of things when we're talking about infinities. We remember if we had the growth being the same, this would dominate the growth of the numerator. This would dominate the growth of the denominator. We would just look at x cubed over 3x cubed. We'd be able to kind of cancel out the x cubes in terms of their growth, and this limit would be 1/3. Do you remember that? Okay. And then, of course, if we are growing faster in the numerator than the denominator, we would be either positive or negative infinity. In this situation, it'd be positive infinity. Okay? Review from Unit 2 way back in the day. All right, let's do some derivatives. Yep. Start with that one. At e should get a value. You might be able to simplify your value, but if you can't, then just leave it as, the sum of two things possibly. We see we have a product. We must use the product rule. In this case, we can simplify. Let's do this derivative. this is acceptable, but I'd probably prefer this. And from this, you would get this if you wanted to, and you can rewrite that like that if you wanted to. Right, because the natural log of e, it's like the natural log of e to the first. The log and e cancel, you just get 1. Question was, why does the natural log of e plus 1 equal 2? Okay, so that's our answer there. Any questions on that guy? Let's do this guy. Let's make this that. And let's make this 2. And let's find this at 1. Sometimes you won't be asked to find the derivative at a point, but sometimes it's easier for simplification's sake to have a point to plug in so that you can see if your answer is right or not. That's fine. Yep. Make sure your derivative is correct. The derivative of 3 to the x squared would be 3 to the x squared, natural log of 3, times 2x. This is the entire derivative of 3 to the x squared. And then I have to multiply it by that other 2x. I wanted to figure this out at 1. It would be 2 times 3 plus 3 times log 3 times 2 times 2. That'd be 6 plus 12 log 3. And you would just leave it like that. That's the derivative of a number to a power. So the derivative of any number to a power is the number to the power times the log of that number, the natural log of the number. Now, the reason why we don't do it for e to the x, and we could, is because you can write it as e to the x log of e. But we know that the log of e is just 1. So since this is just 1, we exclude it from the derivative of e to the power. But if you have any other number, the derivative is the number to the power times the natural log of the number. Shows you how natural logs and e's are kind of present everywhere when we're dealing with powers. Yes?
Wait, where does the first 2x come from after L of 3?
Right here.
Yeah.
So chain rule, right? The derivative of, a number to a power would be a number to a power log the number. But then chain rule says, log the number. Chain rule says we have to then take the derivative of the inside, whatever that power is. So I have the 3 to the power log 3, but then I have to take the derivative of the x squared. The derivative of the x squared is the 2x. Okay. Let's find this derivative. Remember, the derivative of log of stuff is 1 over the stuff. So using the chain rule, the derivative of log of that stuff would be 1 over that stuff times the derivative of the stuff. And if you wanted to put the 8x minus 2 above the 4x squared minus 2x, you could, but you don't have to. Okay. We'll get to those. Yep. Okay. Now you might see these limit questions like this. But these aren't limit questions like the other limit questions that we did. These are actually derivative questions. Because you need to recall that this limit is the definition of a derivative. This is the same as what is the derivative of my function. But if we had a number, like f of some number plus h minus f of some number, that is the same as what is the derivative of my function with x's when x is the number. So what your job is to take this, translate it into this, and then to find the answer. Yes. Questions about that? They may appear a little bit different than that. They might appear like this. This is using the alternate definition of a derivative. The alternate definition of a derivative is the limit as x approaches some number of f of x minus f of the number over x minus the number. And this is translated immediately into the derivative of the function at the number. F of x, f of x. My number, my number, my number, my number, my number, my number. Derivative is e to the x. At 6, we get e to the 6th. Yes?
Can you go back to what we did, the log one?
Sure.
So we took you found the derivative.
Yep.
Y.
Yep.
Wouldn't
Yeah, but it's not the derivative of log of 4. It's the derivative of log of x when x is 4. It goes to this situation. Does that make sense? No. If there was no value, if it was just f of x plus h minus f of x, if this is the log of x plus h minus the log of x, the answer would be 1 over x. I'm replacing the x with the value. That means we're taking the derivative of the log function at 4.
So we don't worry about the 4 until we find the derivative.
Yes. I originally, when doing these problems, thought the way you thought. I thought it's like, oh, this must be the derivative of the log of 4. But no, it's the log function when x is 4.
So we already have the derivatives. The derivative of the problem is log of x.
Now, the derivative of log of x is what I need to find when x is 4. If you think about it graphically, we have the log function at 4 plus h. Well, here's the log function. Okay, at 4, let's say it's right there. At 4 plus h, it's right here. This is like a plus h. Okay, minus the log of 4 right there, divided by h. Well, as h is approaching 0, we have that tangent line. Okay, we are trying to find this slope of this tangent line. It's not just the log of 4, it is the slope of this tangent. It is the slope of log x when x is 4. All right, f of b minus f of a over b minus a. This is 4 plus h minus 4, which is h. You'll get it, Mr. Russell. I believe in you. Okay? I can show you some more proofs as to why. Let's see this one. Questions about that? Okay, 2 more. Implicit derivatives. Let's find the derivative of that. dy dx. Solve for dy dx. Sorry, I shouldn't have that f of x there. It should just be e to the x plus y equals x squared plus y squared. Yep. Right. The derivative of y with respect to x is dy dx. Now to solve for dy dx, in this situation, I can't divide by the e to the x plus y, because then it would trap this dy dx. Instead, I'm going to have to distribute this e to the x plus y. Subtract this, subtract this. Factor out the dy dx, and then divide to solve. I'm going to just do that all in one step.
Why isn't that x prime plus y prime?
Because the derivative of x with respect to x is just 1. You're thinking of taking the derivative of x with respect to a different variable, like t. All right, last one. Any questions on this one? What? What part?
We go e to x plus y after that.
Okay, so it's a chain, right? Derivative of e to the power is e to the power. So I have e to the power here. But then, since I have something other than just x, I have to multiply by its derivative. The derivative of x plus y is 1 plus dy dx. So that's the chain rule. If this was e to the x squared, the derivative would be e to the x squared times 2x. Since it's an x plus y, I need to have the derivative, which is a sum of the derivative of x and the derivative of y. Now, to solve for dy dx, we have a dy dx here and here. I need to get them onto one side. Well, I can't move stuff easily because of these parentheses. So I have to distribute this to remove the parentheses, so now I just have stuff being added. I can subtract this, I can subtract this, so I have this guy minus that guy, and over here I have this guy minus this guy. And then I factor out the dy dx and divide by e to the x plus y minus 2y. Okay? All right, last one. There are multiple ways to solve for dy dx in this case. Yes, sir.
Okay, so on the one where it was find the derivative of the log of x when x was 4.
Yeah.
So you find the derivative of log x first, so you get the 1 over x, and
Yep.
the derivative of x is 1, so you get 1 over x, and you plug in the 4 last.
Yeah, you're just like, the question was essentially, what is the derivative of log x when x is 4?
So you plug in the 4 like very, very fast.
Yeah. It's like if I asked you if f is log x, what is f prime when x is 1? Derivative of log of stuff is 1 over the stuff. I got 1 over the stuff times the derivative of the stuff. Now, in this situation, since I don't have a dy dx on the right side, I don't have to distribute this if I don't want to. I actually could just multiply by x minus y right away. And all of a sudden, I will free up things, and they won't be in parentheses anymore. Then I can subtract 1, divide everything by -1. Yes.
Whatever's the 1 in front of dydx, you have 1 minus dydx.
Yeah.
And then you multiply by x minus y.
Yep.
Doesn't that turn 1 over x minus y into 1? Okay, I got it. Never mind.
There's the 1. Right. You can have 1 here. Okay. Yes.
Would it still be right if you left it as 2x times x minus y minus 1?
Yep.
The opposite.
Right. And it would still be right if instead of doing this, you did what you did in the last problem, which was to distribute. You could distribute this and then solve for dy dx, and you just have a crazy looking fraction. It'd still be right though. Okay. That's it. That's the prep for your quiz. You're going to take the quiz. When you're done with the quiz, you are going to be done with the quiz. You're going to watch the video online. The video is only going to be 15 to 20 minutes, this new lesson. It's actually very easy. Just you got to watch the video. If you don't watch the video of the lesson on inverse derivatives, you're not going to know what you're doing. You're not going to have a good time.